Hey there, we're looking at 6.2 today on solving exponential equations and inequalities. And so our two objectives are to be able to do that, to solve exponential equations and exponential inequalities. And that all leads us back to standard ACE 1, which is to create and solve equations and inequalities in one variable, and that does include exponential functions. And also to interpret their solutions and determine whether they are reasonable. And mainly that is more with a couple of our other types like simple rational functions, which unfortunately we will not get to this year. But let's go ahead and look at a couple of properties here and get into some examples. So the first property we're going to look at is the property of equality for exponential functions. And this property says this. Now remember that exponential functions, the b value, the base, right, has to be greater than 0 and can't be 1. And so you're going to see that in both of these properties that we look at today. But if I have that b to the x is equal to b to the y, then the exponents must be equal. The x has to equal the y. So let's look at the example below. If I have 4 to the x is equal to 4 to the third, then x has to equal 3 because 4 to the fourth doesn't equal 4 to the third, right? And so the converse is also true. If I'm given just that x is equal to 3, then I could make those exponentials by using the same base for both. And that's why you see b for both. It's not like b and c. It's the same base for both parts of the exponential. But that's where our examples are going to take a little bit of a detour. Because when you look at example 1a, it says solve the equation. 3 to the x is equal to 9 to the 7th. Those don't have the same base. But think about this. Can I rewrite 9 as a base of 3? What is 9 as 3 to some power? What power would that be? Well, 9 is 3 squared, right? And so I can rewrite this problem as 3 to the x is equal to 3 squared, and then that's still to the 7th power. Now we're going to use our power properties here to simplify this, and I'm going to get that 3 to the x is equal to 3 to the 14th, because remember, power to power, we're going to multiply those two powers together. And so using our property of equality for exponentials, we're going to get that x is equal to 14, and that is our final answer, that x is equal to 14. And if I do 3 to the 14th in my calculator, and I do 9 to the 7th in my calculator, I'm going to get the same value. It's a very large number, but it would be the same value for both. Let's look at example B. Same idea here, right? I've got 2 and I've got 4. Obviously 2 is the smaller of the pair, so can I rewrite the 4 as 2 to some power? Right, so 4 is 2 to what power? Well, 4 would be 2 squared, right, because 2 squared is 4. And so I can rewrite this problem as 2 to the 5x is equal to 2 squared, and then this power is still here, 3x minus 2. Remember that we're going to multiply power to power. And so I'm going to get 2 to the 5x is equal to 2 to the 6x minus 4. Make sure you distribute that. And then because the bases are the same, I can set the exponential parts equal to each other. And so I get that 5x is equal to 6x minus 4. I'm going to subtract the 6x from both sides. And I get that negative x is equal to negative 4. And dividing by the negative 1, I get that x is equal to positive 4. Now, we could verify this answer here. So plugging in the 4, we're going to get 5 times 4 is 20. So this is 2 to the 20th. And if I come over here, 3 times 4 is 12. Minus 2 gives me 10. That's 4 to the 10th, which would be 2 times 2 squared to the 10th, so 2 to the 20th. Okay? And so it does verify out. And we can check our answer over on the left-hand side too from problem 1a. All right, so that's how we deal with those power properties. Again, with the problems that we're looking at in this section and in this unit, we're not going to get crazy. When we get and talk about logs and we talk about being able to use logs to solve exponential problems, which unfortunately, again, this is one of those things that we're going to hit kind of quickly at the end of this unit in the final week. And so we're going to touch on it just a little bit, but that's where we can get into some values that don't have bases that line up together, like 3 and 9, or 2 and 8, or 5 and 125, right? Because we can convert those down to a smaller base with an exponent. Okay, so let's look at example 2 here. And you're going to see this section, and a lot of this unit is dealing with application. Exponentials are used all the time. And so this is 2020, right? So we're talking about a new census this year, and I hope that your parents have filled out their census, because that does go towards federal dollars that that Kershaw County does get, and the state of South Carolina gets for the next 10-year cycle that the census gives us that for. So on that note, let's look at some population data. In 2010, the population of Kershaw County was 61,706, and this is the actual number according to the census. I looked up these numbers. By 2015, it was estimated by the U.S. Census that Kershaw County's population was 63,661. And so we're going to write an exponential function that can be used to model the population of Kershaw County. And we're going to write t in terms of the number of years since 2010. So let's talk about the information that we know. We know an initial starting value here. We know a final value. And we know how much time it took to get there, right? So when we think about our exponential function, y equals ab to the x. Sometimes you'll see the x written with a t instead, and in this case we are dealing with time, so we'll change that to a t. So what values do we know? We know the final value, which would be our y, right? So this would be the 63,661. We know our a, our initial value, is 61,706. We don't know the rate of growth, because remember the b, if we go back to what we talked about in section 1, is that growth or decay factor, right? And so obviously we're growing, so whatever b value I have will be larger than 1. Again, it's going to be 1 point something unless we're growing at a super fast rate. But obviously we didn't grow and double our population in just a few years. And then our t, 2010 to 2015 is how many years? 5. Okay, so we need to solve this out. And so our first step would be to divide both sides by the 61,706. And when we divide that, we're going to get 1.03168. Now I'm taking this out to quite a few decimal places. Keep all the decimal places in your calculator for the next step, because you want to have as many decimal places as you can for this next step. So this is going to be equal to b to the 5th. Well, we've got an exponent, so how do we get rid of an exponent? We do a radical, right? And so I'm going to take the 5th root of both sides, in this case, because that's our power, so I get left with the b. And so our b is going to be equal to the 5th root, and so make sure you do that right in your calculator to get that 5th root. And we get 1.00627. Okay, again, I'm using quite a few decimal places, and actually the number after the 7 is a 6, so technically that would round to an 8. So with this problem, we're going to round it to enough decimal places that will get precision. And so I'm going to tell you to round this one to this 2 here, so we're going to write it as 1.0063 will be approximately our b. And so what is our function? Y is equal to the 61,706 times 1.0063 to the t. That is our exponential function that models the population of Kershaw County since 2010. Now, Part B asks us to predict what the population will be in 2025. Well, how many years is that since 2010? Well, that's 15 years. And so this next part is very straightforward. Y equals the 61,706, 1.0063 to the 15th. Now, if you kept all those decimal places in your calculator, that is great. Use your calculator storage to keep as many decimal places as possible, because that will give you a more precise answer. And I'm going to show you why that matters, especially as we use very large numbers. Rounding errors come into play. And so I'm going to first do this with the entire decimal that my calculator gave me. When we do that, I get y would be equal to 67758.6 0.78, and so obviously we can't have 0.78 of a person, so we'll round that up to 67,759. If I do that with just this number, let's see what we get. And so again, we're looking at y is equal to the 61,706, 1.0063 to the 15th. Now, remember, this number was 6254. This is 63, so this is going to be a little larger because we're dealing with a larger growth factor, technically, in our calculation. And so the number I get is 67,801.53. That's 28 and so on, so we'll round to the 3. And remember, we can't have a partial person anyway, so 67,802. So we see, depending on how precise we round our answer, will determine the precision of our calculation. Now, here's what we need to remember. Our precision of our answers should come back to our significant figures of our numbers that were given. We were dealing with a 5-digit number here, and so if I deal with just the 5-digit number, this is the value we're getting. But again, we're seeing that as a population difference of just under 50 people. And again, that doesn't sound like a big deal, but again, that's the difference between districts being formed one way or another, or when we talk about representatives in the U.S. House, that is the difference between, the state of South Carolina having 7 districts or 6 districts or 8 districts, because again, it's all based on population and how we compare to other states to divvy up the 435 U.S. House members. So just little things to think about as we talk about population models. All right. So let's talk about another type of exponential function, and this is compound interest. And this is one that will boggle your mind. And had we had class together, I would encourage you, and I'm going to put this link in Google Classroom for y'all to go watch. It's a little 3-minute video, and some of you may know Dave Ramsey, but I'm going to link that video in Google Classroom for y'all, talking about compound interest and how if you start saving now, you will see a huge difference in what you'll be able to make and save through the years. Again, it's a really good video, about 3 minutes, and just a little extra for y'all. But let's talk about compound interest and how it works. So here's the formula. A is equal to P times 1 plus R over N to the NT power. And I've listed out here what all those variables stand for. A is the amount that you'll have after T years. P is your principal, which is the initial amount that you invest. R is the annual interest rate, and of course we'll convert that rate to a decimal to be able to work in the problem, not as a percent. N is the number of compounding periods annually. And so if we talk about compounding monthly, right? If we talk about compounding monthly, how many months are there in a year? 12, right? So my N would be 12. If I talk about compounding quarterly, let's spell that right, quarterly, how many quarters of a year are there? Well, there's 4 quarters, right? If we talk about doing it daily, right? If we're dealing with only 1 or 2 years, we'll typically use the 365. If we know we're dealing with a leap year like this year, we'll deal with 366. And that would change our calculation slightly. If we're dealing with decades, but our interest is compounding daily, we will actually use 365.25 to account for that leap year every 4 years, because that takes care of that extra day every 4 years. And T is the number of years. So if I'm doing this for 5 years or 10 years or 28 years, we would plug in that for T. Okay. When we get to, and again, something that we're not going to really get to, but if we talk about the natural base, E, that would get us to compounding interest that compounds continuously. So as soon as you earn any interest, you would deal with that. But that's a whole nother formula for a whole nother time. Okay, so let's look at this example here. An investment account pays 4.5% annual interest compounded quarterly. If $5,000 is placed in the account, find the balance after 10 years. And then find the balance after 25 years. And so we're going to use our formula. A is equal to P times 1 plus R over N to the NT power. And so a is equal to p times 1 plus r over n to the nt power. I always like to copy the formulas because it just helps me plug things in the right spots. So let's understand what we're given. We're starting with how much money? $5,000. So this is my p. My annual interest rate is 4.5%, so that's going to be 0.045. That is my r. We're told it's compounding quarterly, so my n is equal to 4. And then we're actually doing this problem twice. We're going to first do it for 10 years, and the second is we're doing it for 25 years. So both of those would be my t's. This is t sub 1, this is t sub 2. And so, again, we're going to do this problem twice. A is the amount that we're finding. What's the balance, right? What's the balance? That's our A. So this would be A sub 2. This is A sub 1. Okay, so A sub 1, this would be the 10-year mark, right? So we're going to start with our $5,000. It's 1 plus 0.045 over 4, our number of times we're compounding, times 4 times 10. And so our calculation here, 5,000, 1 plus, when we divide that, we get 0.01125. Keep all the decimal places here, please. Do not round this. And 4 times 10 is 40. And so we're going to get A sub 1 is equal to 5,000, 1.01125 to the 40th. And so when we plug all that in our calculator, this is not something you need to show this middle step here of what is 1.01125 to the 40th. Just type this entire thing in your calculator and get that our final amount here after 10 years is going to be $7,821.88. Again, if we're dealing with money, 2 decimal places. If we're dealing with people, no decimal places, right? Understand what we are dealing with. So after 10 years, so again, this is our 10-year mark, our account has $7,821.88 in it. We've gained $2,800 in 10 years just by putting $5,000 in this bank account or in this whatever account, in this investment account to earn. But what happens if we let that money continue to sit, continue to gain this interest for 25 years? Let's watch what happens. So A sub 2 is equal to our principal, still that initial $5,000. I haven't put any extra money in. 1 plus, it's the same interest rate. It's 0.045 over the compounding of 4 times a year because it's quarterly. And it's going to be 4 times the 25. And so what we get, there's our 5,000. Inside's still going to be the same, so 1.01125. That part didn't change. But our exponent is now 100. So I've gone from compounding this 40 times in 10 years to 100 times in 25 years. And so that's going to change our amount. And so when we get that 5,000, 1.01125 raised to the 100th power is going to give us $15,304.65. So again, if we let that money continue to sit for another 15 years, we're going to just about double our money. It's a little short because it'd be 15.6 if we doubled it. So doing nothing, letting this sit and earn interest, we've turned $5,000 into $15,000 just by letting it sit in an account for 25 years. And that's the point of compounding interest. That's the point of why, hopefully your parents or your guardians are wise and tell you to start saving now. Because if you start saving now, again, this is that Dave Ramsey video I want you to go watch. If you start saving now, it's the power of compounding interest that is going to save you when you are older than I am now and older than your parents are now. Because it'll let you retire a lot earlier if you have done things wisely. Make smart choices with your money. All right, so getting off that high horse there, but I think it's important that you understand that the more something compounds, it also affects it, right? So if we were to go back and do this problem quarterly and then we do it monthly, right? We could change this number, right? So we're going to be dividing this by 12 because it's monthly, but we're going to be taking our power to 12 times our number of years. And so it changes the number of times we compound in our set time frame. And so again, you'll see a difference in the amount. Smaller amounts, smaller percentages won't be as much, But again, if you're dealing with 4, 5, 8, 10, 12% over those monthly compoundings, then you're going to gain that a lot sooner. Okay. All right, so we've talked about equations all the time. We're going to talk about inequalities real quick here with about the last 5 minutes of this video. But the steps are the same as everything else that we've done so far. It's just a matter that we're dealing with an inequality. And so the property says this, again, dealing with that b has its restrictions, that has to be positive and not equal to 1. If b to the x is greater than b to the y, then x is greater than y, and of course that flips because of our if and only if statement, because remember this is a two-way street when we use that notation. And if it's less than, and of course our exponents would be in their same order, x less than y. And so we see it with the example here, 4 to the x is greater than 4 to the third, so x has to be greater than 3, right? Because 4 to the fourth would be greater than 4 to the third, right? Because 4 to the fourth is 256, 4 to the third is 64, right? And so let's solve this exponential inequality here. Again, the steps are the same, but I don't see a 5, right? You're like, wait, where's the 5? Where's the 5? Well, we're dealing with 1 over 625. So the question becomes, 625 is 5 to what power? 625 is 5 to the fourth, but it's in the denominator, so that means this is 1 over 625, which means it's going to be 5 to the negative fourth power. And so I'm going to write 5 to the 3 minus 2x is greater than 5 to the negative fourth. And so because the bases are now the same, I can compare the exponents. So 3 minus 2x is greater than negative 4. I'm going to subtract, sorry that's sliding on y'all there, the 3 from both sides. And I get negative 2x is greater than negative 7. I'm going to divide both sides by the negative 2. And remember that when we divide an inequality by a negative on both sides, we are going to flip that inequality, so x is going to be less than 7 halves, or x is less than 3.5. And so we can test that out if we were to plug in 3, right? So we get 3 minus 2 times 3, so that's negative 3 in the end, because 3 minus 6. And so 5 to the negative third is less than 5, is greater than 5 to the negative fourth, because 5 to the negative third would be 1 over 125, and that number is larger than 1 over 625. Okay, and so that's it. This will be our final answer here. Again, not complicated if you just follow the steps of solving equations, right? Go back and solving inequalities to PEMDAS. Remember, if we're solving, we are working up. We are getting rid of addition, subtraction first. We're getting rid of multiplication, division. We get rid of our exponents. We get rid of things inside of parentheses. That's our goal. So the word of the day is exponential. Again, the word of the day is exponential. I hope y'all have a great day. Again, if you have questions, make sure you hit up that Google Meet. Make sure you email me first before you try to join, because if you try to join before I do, it's going to kick you out because the teacher has to be in first. So again, make sure if you need help, contact me. But I hope y'all have a great day. And again, I'm here for you if you need me.